Hello, I'm Shamik, and I'll be presenting our work, DDoS-UNet, incorporating temporal information using Dynamic Dual-channel UNet for enhancing super resolution of dynamic MRI. MRI can provide high spatial resolution and superior visualization of soft tissue contrast. Interventional applications of MRI, such as MR-guided liver biopsy, show excellent contrast between the target organ and adjacent soft tissue while visualizing the changes in internal organs. In such applications, dynamic MRI is used, which is obtained by acquiring the case-space data continuously and reconstructing a sequence of images over time. However, while achieving high temporal resolution, these acquisitions suffer from restricted spatial resolution, known as the spatio-temporal trade-off. This research aims to resolve this trade-off by performing super resolution of MRIs using deep learning by exploiting the present temporal relationship. For the same, we have proposed DDoS-UNet, which is a multi-channel unit that receives low-resolution input image along with a high-resolution prior image as input and provides the super-resolved image as output. This output, along with the ground truth, is supplied to the perceptual loss network to extract the features from both of them. Finally, the features obtained from these two are compared using L1 loss and then summed up to obtain the final loss, which is then backpropagated to train the model. During training, the network is supplied with an artificially created dynamic dataset. For every time point, a low-resolution version of the current time point is supplied as input to the model, while supplying the high-resolution previous time point as a prior image. Then the model super-resolves that input, which is then compared against the ground truth to compute the loss, as I mentioned before. During inference, the model is supplied with the first low-resolution time point, along with a patient-specific high-resolution static planning scan as prior, and then the model super-resolves this first time point. We refer to this phase of inference as the antipasto phase. Once the initial time point is super-resolved, it is then supplied as a prior image with the next low-resolution image to super-resolve that. The process continues in this recursive manner till all the required time points are super-resolved. We hypothesize that the network learns two different relationships: a super-resolution relationship between the low-resolution and high-resolution images, and a temporal relationship between the current and the previous time point. For our approach, we have used the publicly available chaos dataset and then artificially created the chaos dynamic dataset. For evaluation, we obtained static and dynamic MRIs of 5 healthy subjects using 4 different protocols. For the experiments, we undersampled the acquired dynamic scans by taking 10%, 6.25%, and 4% of the center of the case space, resulting in theoretical acceleration factors up to 25. The acquisition protocols can be seen in Table 1. Table 2 shows the theoretical acquisition times for each of those undersampling factors. For example, the highest acceleration experimented during this research has the potential to reduce the acquisition time for one time point from around 9 seconds to little more than half of a second. The chaos dynamic dataset was created by applying elastic deformation of torch IO with 5 control points and 5, 20, and 20 mm maximum displacements along X, Y, and Z dimensions, which was then applied using cubic B-spline. For training the model, we used perceptual loss as mentioned before, and this was optimized using the Adam optimizer with a learning rate of 10 to the power minus 4 for 100 epochs. Now let's have a look at the results. We can see that the proposed DDoS-UNet improved the image quality considerably better than the normal UNet model. The zoomed-in patch shows us that the DDoS-UNet results are very close to the ground truth. Let's have a closer look at the highest undersampling we experimented with, which was 4% of the center case space. We have compared against 2 different UNet models, one trained with the chaos dataset and the other one trained with the artificial chaos dynamic dataset. 2 different regions are marked by yellow and green and zoomed in on the right side. It can be seen, especially as pointed out by the difference images J and L, that without the help of temporal prior, the UNet models did not manage to super-resolve the low-resolution image as close to the high-resolution ground truth as the DDoS-UNet managed to do. The quantitative results confirm the findings of the qualitative results regarding the superiority of the DDoS-UNet over the baselines. Statistical tests determined these improvements to be significant. And we can say that the temporal information really helped the model. But as we are working using the previous super-resolved time point as prior in a recursive fashion, it might also accumulate the errors. To verify this, here we have line plots for each time point. We can see the results of the first time point is not very good, similar to the other models actually, which was the antipasto phase. Then for the rest of the time points, the results are very stable and always better than the baselines. We also do not see any trend which suggests that the DDoS-UNet deteriorates over time. Now to conclude, we propose the DDoS-UNet here to perform 3D volumetric super resolution of low resolution dynamic MRIs by using a subject-specific high-resolution prior planning scan and exploiting the spatio-temporal relationship present in the dynamic MRIs. The proposed method resulted in 95% SSIM value while super-resolving the highest undersampling experimented here. In future, a dual-branch strategy to supply the prior image will be explored. Moreover, DDoS-UNet is interesting in interventional setups. During interventions, devices such as catheters are used, which were not present in the training set. We plan to extend the current research by evaluating the proposed model's reconstruction performance for such devices. And finally, here is the link to the GitHub code of this research. Thank you so much for your attention and feel free to contact me for any questions or feedback.